Welcome everybody. Thank you for coming up to join us. It's been 2.5 years since we had our last public programs here, so look around the room, nobody has aged a bit. So my name is Paul Lyon, and I'm one of the astronomers working and living here on Mount Hamilton. It's delighted to have a community of people coming back because we've had some crises we've gone through. Some of you may have heard the stories. Fire, pandemic, we're waiting for a plague of frogs next. Just want to thank you for your support. I know lots of you have been following the story of Lick, maybe not for the 130 plus years, but certainly in the recent years. Thank you for your support, and thank you for spreading the word, and we're very proud of what we do, and we hope to continue for another century at least. We really need you to take that advocacy into the local community, in particular things to do with light pollution, for example. We know that we have developments going on. You may have seen issues in the media about that. We have Google doing some sterling work and relocating a campus, also hopefully bringing responsible lighting to San Jose and so on. So we encourage you to continue to advocate for the observatory, and if you don't have a nice time here tonight, if you don't find it interesting, well, tell me or tell somebody with a badge, and we'll do our best to try and make it better for you. If you do have a good time, please go on your favourite social network, tell everybody about it, because we do need your assistance in spreading the word. You can also consider joining an organisation. I'm sure many of you, I see some familiar faces, are already members of the Friends of Lick Observatory organisation. That's another way to help us out and give us a bit more material help. And you can also consider donating and so on. But we're not going to labour that horse today. We're running slightly behind time. I want to introduce our distinguished speaker tonight, who graduated in with a PhD from Princeton University, which is very impressive. He joined the University of California, Santa Cruz in 1997, and I believe still serves presently as chair of the Department of Astronomy and Astrophysics down there. So he might refer to his present sentence. Roger is an expert on galaxy formation and evolution, particularly on nearby galaxies, our own Milky Way and the Andromeda Galaxy. As I mentioned, he's also a great counsellor and has advised for decades on advising local authorities about light and responsible lighting and light pollution and so on. He's a passionate advocate for education for all, and he's led the way in mentorship programs in UCSC and beyond, and we should thank him for that. And quite aside from all that, if he's not achieved enough, he's actually a very, very talented artist and a delightful colleague. And tonight he's going to speak to us on the darkest secrets of the universe. Professor Roger.
Thank you, thank you. Thank you, Paul, and thank you, Ellie, for your, and I apologize for the jangled nerves and the traffic jam at the base of Mount Hamilton Road. The number that Paul was getting stuck on was 1989. That's when I got my PhD. And I actually started in Santa Cruz in 1994, a full 3 years before Paul gave me credit. Okay, so I've been around 28 years in this department. And yes, my sentence as department chair is going to end in 1 day short of 13 months. So I'm counting. I can tell you the number of hours, but I won't. I want to talk about galaxies, and almost every point of light you see in this image is a galaxy, nearly every point of light. The one with the crosshairs near the top right is a star in the Milky Way, but pretty much everything else here that's obvious to your eye is a collection of stars. It's a distant galaxy. Is my audio okay for all of you? Back in front? Okay, great, thank you. The colors in these images mean something. So when something looks an intense orange or yellow, like this galaxy that I'm pointing to, it means the stars have relatively low surface temperatures, lower than the sun. And that typically signifies an old galaxy that hasn't formed stars in recent times. You see several of these orange, red-looking things, and when you see something that's bluish white, it means that such galaxies are actively forming stars, were actively forming stars when light left them. So I'll talk about a couple of kinds of dark secrets of the universe. It's very J.K. Rowling and Harry Potter-esque because, it's the universe is about tussle between two dark forces, dark matter and dark energy. And I'll talk about these things, and just want to give credit to Google. I was visiting faculty at Google for 8 months in 2015, and they helped me a lot with some of the outreach work that Paul referred to. I'm going to motivate why galaxies are important. We know that atoms are basic building blocks of the universe. In the same way, galaxies are basic building blocks. Atoms are basic building blocks of matter, and indeed of all matter in the universe, but galaxies are basic building blocks of the universe itself. And there's something that's nicely parallel between these two things. Atoms are not the smallest subunits of matter. Atoms can be broken up into protons, neutrons, and electrons. Protons and neutrons can be broken up into quarks. So atoms are not the smallest units, and they're certainly not the largest units. In the same way, galaxies are neither the smallest nor largest units, but they're important because if it weren't for galaxies, and weren't for the fact that we live in one galaxy, like the Milky Way, we wouldn't have complex life here on Earth. Okay, and I want to spend the next slide talking about, trying to explain why galaxies are related to complex life. And I'm going to talk about your place, my place in the cosmos. When you think about your place in the cosmos, you might think about yourself, you might think about loved ones. I think about my son lounging on a carpet right there. I'm also thinking about human life forms and viral life forms. That inset shows the dreaded coronavirus and a person supposedly infected with the coronavirus. So the story about complex life, by complex life I include all three of those life forms. Viruses all the way to mammals. That sort of is the range of life forms we're familiar with here on Earth. What's common to them is they're made up of complex molecules like DNA and proteins, and this is a representation of a molecule that has thousands of atoms, and every colored sphere there represents a different atom in the periodic table. Now, in order to form molecules of this size and complexity, you need atoms that are somewhat deep into the periodic table. They can't be the very first atom. The very first atom, hydrogen, has one electron, so it can literally form a bond with one other atom. And so it can't be the central atom of a complex molecule like this. It can be at the periphery, but it can't be a central atom in this. Helium has 2 electrons, so it can hold 2 hands at once, but helium doesn't like to hold hands at all because it's an inert atom. So, lithium comes next, beryllium, boron, carbon. We often talk about carbon-based life, and I'm going to talk about carbon, nitrogen, and oxygen because they are essential elements of organic molecules that make up living things like us. And I think it's fair to say that the complexity of these organic molecules like proteins and DNA are directly related to the complexity of life. Complexity, richness, diversity of life. They're related to the fact that they're made up of complex molecules that can be oriented in multiple ways. So we know the Earth contains these elements, C, N, and O. We're breathing carbon and oxygen right now. Oxygen is present in our oceans. However, we for a long time didn't understand how these elements made it onto the Earth. There was a natural notion, once people realized that stars are nuclear reactors, nuclear fusion reactors, a question was asked that did our sun produce the atoms that we enjoy here on Earth today? It's a natural question to ask. It's the only thing near us that's producing atoms, so did it produce the atoms that's here on Earth today? And the answer to this question, surprisingly, is no. The sun is producing atoms, but it's only producing helium from hydrogen. That's the only thing it's doing. It's not producing any carbon, nitrogen, and oxygen in substantial quantities yet. It will at the end of its life, but it hasn't done so yet. So, how we came to be and how complex atoms came to be, the answer to that question isn't answered by the sun. We have to look before the sun. We have to look in time further back than the sun. It turns out that these complex atoms that you and I are made of are actually some kind of stardust left over from previous generations of stars that the sun and solar system planets were formed out of. In other words, these atoms are part of our inheritance. Our Earth was born with these atoms. Now, these atoms, I say, came from other stars, the sun's ancestral stars, and the sun's ancestral stars came in a variety of sizes, not shapes, they're all spherical, sizes, masses, temperatures. And this star field here gives you a sense of the diversity of star types that exist in our Milky Way. In some of these stars, the ones that look bluish-white, like some of the stars in the lower left corner, stars that are bluish-white shine more intensely than the sun, and that's because they're undergoing nuclear fusion much more rapidly than the sun. The sun has already spent half its life, about 5 billion years, converting hydrogen to helium, and it's going to spend another 5 billion years or so doing the same thing. These stars can finish up all their hydrogen, convert it all to helium, go from helium to lithium, beryllium, boron, carbon, all the way to the 26th element in the periodic table in a matter of less than 1 million years. Less than 1 million, whereas the sun has taken, or will have taken, 10 billion. Now, only the most massive stars can do this in 1 million years, but it's more common for things to take 4, 5, 10 million years, even 100 million years. It's stars like that that lived and died before the sun and solar system were formed that's responsible for us here in this room. Now, it's not enough that these massive stars are very efficient at producing elements. They're also very generous. At the end of their lives, they explode. And I'm calling that generous because that takes what was produced in the star, releases it to the surroundings so that the next generation of stars can benefit from that chemistry. This is a picture of an exploded star seen as it looks about 1,000 years after the explosion. The explosion actually does two very important things. Dispersal is one of the things, dispersal of elements, but there's so much energy available during explosions that the rest of the elements in the periodic table, ones beyond the 26th element, iron, can be produced during explosions. They can be produced in other energetic phenomena as well, like the merger of neutron stars and explosions that result from that. But massive stars exploding is certainly one channel through which the rest of the periodic table is produced. Now, these things are, as you can probably tell from this picture, these things are very energetic. So when you have an explosion of that kind of energy, you need a big galaxy with lots of gravity, lots of dark matter, to rein in that explosion. Otherwise, it's no good if the star explodes and all of these elements that it produced are blasted right out of the galaxy. The next generation of stars is not going to benefit from it, you see. So, not only did we need to be part of a galaxy, a massive galaxy, it had to be a massive galaxy with lots of, this invisible dark matter whose gravity was capable of reining in explosions of massive stars. So, the path to finding our origins of complex life on Earth, actually leads us to massive galaxies and dark matter. So for all this to happen, we really had to be part of a large galaxy, and this is not a picture of the Milky Way. You may have guessed this already. We live inside the Milky Way. We don't have long selfie sticks. So this is a picture of our neighbor. This is the Andromeda Galaxy. So we can look, astronomy is... Astronomy is sort of unfortunate. An astronomer is like a person stuck in their bedroom their entire life. You can't leave your room. You're lucky that the walls of your room and your house are translucent, so you can sort of see through your house, but not completely. You can really see your room, but you can't see the details through the rest of the house. You have a sense that there are many other rooms in the house, and you have a sense of the inside of your house, but you've never been able to see it from the outside. So the best you can do is look out of your window, and there are windows in your room, and look at your neighbors, the neighboring houses, and that gives you a sense of what the Milky Way might look like from the outside. That's what we're doing here. Okay, this is a picture of our Milky Way analog seen from the outside. If this were the Milky Way, we don't live in downtown Milky Way. We don't live in rural Milky Way either. We live in some perfectly average part of the Milky Way. Okay, so on this scale, light would take 100,000 years to travel across the long axis of the rectangle, 100,000 years. Light travels fast. Light travels around the Earth 7 times in 1 second. But it would take 100,000 years to go from the right edge here to the left edge of that rectangle. And our sun and solar system, I don't know if you can see, but the sun and solar system are drawn at the center of that square. I'm only kidding. They're smaller than a pixel, so yes, they probably are drawn over there, but we can't see it. Our sun and solar system is about 1 day of light travel time across. But to go from the solar system to the center of the Milky Way would take 25,000 years, traveling at the same speed. That's why you can't see a light day smaller than a pixel when I'm trying to show you 100,000 light years of galaxy. A galaxy like the Milky Way and Andromeda contains about 100 billion stars. 100 billion. And what's this business about dark matter? Let me explain that in just a few sentences. 100 billion stars, that's 1 with 11 zeros, of course, pack a lot of mass, pack a lot of gravity. And based on that, the stars come in a variety of masses, of course. They're not all the same mass as the sun. But on average, the average mass of a star in this galaxy is about the same as the sun. So if you take the mass of 100 billion stars and you ask, how much gravity does it exert on itself? How fast should this galaxy be spinning? You would calculate that Andromeda should be spinning at about 80 kilometers per second. That should be the speed of the sort of frisbee speed, 80 kilometers per second. Now, there was a very famous scientist named Vera Rubin who went out and measured how rapidly Andromeda was spinning. She did this math of how many stars there are, how fast it should be spinning, and her jaw dropped when she found that Andromeda was spinning not at 80, but 250 kilometers per second, 3 times faster. And the way the math works out, it means Andromeda has 10 times more mass than you would give it credit for if you just counted up how much light there was and how many stars that would correspond to. So there's 10 times more material in the form of dark matter, mass that does not produce any light, than there is in the form of stars. And to be fair, when Vera first made this discovery, she found it in Andromeda, she found it in a bunch of other galaxies as well. So it wasn't just something wonky with this galaxy. And other people measured the same thing, and they realized there was nothing wrong with Vera's measurements, but we just didn't understand what was going on. Initially, it wasn't called dark matter. People called it missing mass, the mass that's producing speed, but not producing any light. Today, we know it's not missing mass. It's not the mass that's missing. It's quite very much there. It's the corresponding light that's missing. So it's dark matter. It's matter that's putting out that it's exerting gravity but not putting out any light, not even reflecting light or interacting with light. But it's super important because without that, supernovae would explain, supernova explosions, exploding stars, would clean escape, the material would clean escape from our galaxy and we wouldn't be here today. Okay. All right, that's a long explanation for why galaxies are important. I want to spend the rest of my talk saying a little bit about the lives and times of galaxies, how they form, and in fact that story will take us back, very far back in time to the beginning of the universe. Okay, you can take pictures of the Milky Way from the inside. It just looks funny. It's just like you can take out your camera and take a picture of your house from your bedroom. It'll look funny. This is our Milky Way galaxy. It looks like a band of light. And what I'm going to show you is a time lapse put together by John Rockman, the Castlear School. He took this from a game park in Kenya. So many things will happen as this time lapse plays. One is you can see this tree is lit up by some light source. Someone will turn off the lights at some point because it's getting late into the night. The sky will get darker. And I'm going to remove the label so you can see the movie play. The sky is going to get darker and darker. You'll see shooting stars, you'll see lightning, clouds, the trees fluttering in the breeze, but someone will turn off the lights at some point and the tree will go dark. There you go. But the Milky Way appears to sweep across the sky because of the rotation of the Earth. Okay? And it's not actually spinning, it's the Earth that's spinning. The thing we're looking at it from is spinning. I'll play it one more time. The shooting stars are really beautiful at the beginning of that. Lightning, you saw another one. So this is about roughly a 4-hour time lapse, 4.5-hour time lapse, consisting of a series of 30-second exposures with gaps. Small gaps, no more than 30 seconds. Okay, let me see if I can get this one to play. This is a different kind of time lapse. So here, what the person did was, they said, I want the Milky Way to stay steady in my camera. Let's see what else happens. This is a better view of what's actually going on. The Earth is spinning. I love this. This is Arjen Narenberg's time-lapse video, where he rotates the camera relative to the Earth so to keep the Milky Way static. You'll see planes going over, you see telephone wires, you see all kinds of things, but you see the rotation of the Earth in a way that is very hard to see otherwise. This is a time lapse also, as you can tell. All right. Now, we've been talking about ancient history, billions of years. I want to bring us back closer to the present time, to about 250 years ago, when this very famous person, he posted this selfie sometime in the 1750s, 1755. This is Emmanuel Kant, arguably the most famous philosopher of all time. We're talking about his work 250 years after he wrote about it. He lived for 80 years. He lived in, what is Königsberg called now? Kaliningrad, I think. It's in Russia. It used to be in Prussia. And Kant was a philosopher. And among other things, he thought hard about the nature of the universe. And by then, people knew there were these sort of what looked like islands of light, and he called them island universes. So islands of light separated by vast amounts of empty space that he likened to an ocean. So island universes. I've been fascinated with this term, island universes. This is part of my research, is in understanding whether galaxies are really island universes, or how much empty space there really is between our galaxy and Andromeda and other such galaxies. Now, Kant is really famous for this term. He's famous for many other things. He really is a famous philosopher. And he was very humble. He claimed that island universes was coined by other people before him. Most people credit Kant with this great description, really. It's just 2 words, but it really captures the spirit of what we now call galaxies. I have to tell you a story about Kant that I learned from my friend at UC Berkeley. Kant ultimately got a faculty position in the philosophy department at the University of Königsberg. Ultimately. The first time he applied for a job, they turned him down. Now, we're talking about the most famous philosopher of all time, and a small town at the university. They really blew it the first time. Now, I was also turned down for my first faculty position. It was at UC Santa Cruz. I tried in 1993. They gave me a nice pat on my back and said, apply again next year. I did, and I got the job. But, thank you. So when someone gets hired, no, this doesn't tell the full story. Turned him down the first time, but he was later hired. But when someone gets hired as a faculty member, the university has to put aside money for your salary, right? With the tenure system, I don't know if there was a tenure system in Kant's time, but now there is. So they have to pay your salary for as long as you're doing productive work at the university. But more than that, they have to put aside money so you can do your research. So it's called startup money, so you can start up your research at a new place. And for me, it was access to telescopes, access to computing, those kinds of things. Now, if you're a theoretical physicist, your startup package looks like a desk, a chair, a notepad, a piece of paper, and a wastebasket. If you're a philosopher, you don't even need the wastebasket. Now, Kant's work was forgotten. It was forgotten for about 150 years after his writing. So, 1750, add 150 years, early 1900s, beginning of the 20th century, this idea of island universes was rejuvenated by two people. This man here, Harlow Shapley, and Herbert Curtis. Curtis and Shapley were debating the nature of the Milky Way. Shapley said, all these little islands you see, island universes, they're all inside our Milky Way. And Curtis said, no, they're really far away. They are like our Milky Way. They're not inside our Milky Way. They're like our Milky Way, but they're very far away. As with many such debates, they were both right. There were some of these island universes were many galaxies inside our Milky Way. So Shapley was right for that part. But mostly, Curtis was right in that most of Kant's island universes were large galaxies like the Milky Way that were located very far away, well outside the bounds of the Milky Way. So, in most people's minds, Shapley lost the debate. He was wrong. Yet, he was on the cover of Time magazine. He was. It says, I don't know if you can read it, says Harvard's Harlow Shapley. Maybe the fact he was at Harvard had something to do with them putting him on the cover of Time magazine. But Time realized they'd made a mistake. And they weren't going to put Curtis on the next cover because, you don't want to waste magazine covers on astronomers. So they had a standard cover. This was the next issue. This is a more standard Time magazine cover, different kind of star. This is Jean Harlow. And notice that her last name, Harlow, is the same as his first name, Harlow Shapley. And inside the magazine, they refer to Jean as the shapely Harlow. This was a direct play on words. It was a dig at themselves for having made a mistake and put the wrong person on the cover. Anyway. She had nothing to do with astronomy. He did. I did want to show you this picture. This was at the center of the Shapley-Curtis debate. They were trying to measure distances to star clusters like these. This is a cluster of stars. It's not a galaxy. It's a cluster of stars called a globular cluster. And Shapley spent a lot of time trying to measure distances to globular clusters. Now, if you have a keen eye, you will have noticed something about this. This is a time lapse you're seeing. It's not a single picture. I'm going to point my finger to this star over here. And you notice it's going through a little heartbeat. It's getting brighter and fainter, brighter and fainter. Even though this is a looping time lapse, even if it weren't a looping time lapse, these things vary periodically. They go up and down in brightness. These are stars called Aralari. They actually pulse. They physically pulse because instead of having a static balance between gravity and nuclear fusion, they've achieved some kind of dynamic balance, like a oscillating pendulum. They've achieved balance, but a dynamic balance. And there are many of these. This one here that I just pointed to, but there are many others. This one right here. This one here. You'll notice they all have the same sort of bluish green color, and they're all about the same brightness. They're not the brightest stars in the cluster, but they are super important because the fact that they pulse like heartbeats make them very easy to find at large distances. This is a time lapse of these so-called Aralari stars, pulsing stars. And M3 is the romantic name that astronomers have given this beautiful star cluster, Messier 3, third object in the Messier catalog. Now, let me see if there's, yeah, okay. So, my student, Yuting Feng, a PhD student at UC Santa Cruz, is looking for these Aralari stars. They have two properties. One is they pulse. The second thing is they all come with the same wattage. They're all the same brightness. So once you find them, and you can average over their pulsation, but just knowing their average brightness tells you how far away they are. Now, if this is an artist's impression of the Milky Way, again, the size of this thing is about the bright part of the disk. The diameter is a little under 100,000 light years. This is the location of our sun, about, not to scale, I should have had, about 25,000 light years from the center of the Milky Way. Now, if I take this and I shrink, first I rotate our Milky Way galaxy, and I shrink it. On this scale, these are the stars that my student Yuting has found, Aralari he's found, on that scale. So instead of being 100,000 across, these are more like 1 million, about 10 times further away from the center of our galaxy than the diameter of our galaxy, the known diameter of the bright part of our galaxy. So our galaxy is huge, is what I'm trying to say. And let me put it another way. Kant was wrong. Galaxies are not islands. They're about as big as the distance to the nearest galaxy, nearest other galaxy. So galaxies are huge. Now, you can see very clearly that the density of stars falls off with distance from us. That's not a selection effect, that's not a measurement bias. It's the actual density of stars falling off as we get further and further away from our galaxy. So these things are not some kind of contaminant floating through the universe. These things care about our galaxy. They have a density profile that suggests that they know about our galaxy. Their density is falling off. We are in the process of using telescopes in Mauna Kea to measure velocities of these galaxies. They're about 1 million light years away compared to 100,000 for the diameter of our bright part of our galaxy. So again, if this diameter is 100,000 light years, this is about 10, they are about 10 times further away, about 1 million light years. About 40 times the distance of the solar system from our center of our Milky Way. That's Yuting. Emily and Yuting and Eric and I are trying to measure velocities of stars. Emily is a former PhD student at UCSC. I'll show you a few pictures, and of people, not just of galaxies and stars, because it's people making these discoveries. I've also been obsessed with the Andromeda Galaxy. This is a series of 4 mosaics of the Andromeda Galaxy that my students and I put together 30 years ago. Same image, 4 different contrast levels. I'm going to get rid of 3 of them, shrink this one. And on this scale, this is how big Andromeda is. This is now the work of the PANDAS collaboration, Pan-Andromeda Archaeological Survey. That grayscale is a map of stars around Andromeda. With other students, I've gone and measured how fast these stars are moving and whether they really are stars in Andromeda. And we've confirmed again that the density falls off with increasing distance from Andromeda. It gives you a hint that these stars do care about and belong to Andromeda. This is the work, this is now, again, going out to about nearly 1 million years. So Andromeda is about as big as we are. And Andromeda is 2.5 million light years away. If our galaxy's radius is 1 million, its radius is close to 1 million. There's hardly any empty space. If we are island universes, there's very little ocean between us, very little empty space. Again, this is the work of Carrie Gilbert and Alice Thiessen. Alice was a postdoc at Santa Cruz. Carrie was a grad student. Carrie's on the staff in Baltimore, the institute that runs Hubble and is now monitoring JWST. And Alice is a professor at Durham University in the UK. David Reitzel runs planetarium shows for the Griffith Observatory in Southern California. He and I really started this work together as part of David's PhD thesis. All right, a little more about galaxies. This is a beautiful picture of Andromeda taken by Robert Gendler. You can see two of its satellites there, two mini galaxies that are orbiting Andromeda. One at sort of 4 o'clock from its center, 5 o'clock from its center, one at 12 o'clock. And I'm going to superpose this picture on a Mauna Kea Sunset. This is a Mauna Kea Sunset photo taken by Laurie Hatch, who was a resident of this mountaintop, a very talented photographer. And the reason this particular mountaintop is because this houses some very powerful telescopes. Mauna Kea is home to the Keck telescopes. We've been using Keck to study the outskirts of Andromeda and the Milky Way. I want to show you another view of Andromeda, and this crime scene outline around Andromeda, this chalk outline, is a region of Andromeda that we've taken pictures of with Hubble. To scale, that's the full moon in terms of apparent size in the sky. It took 4 years and 828 orbits of Hubble around the Earth to put together what I'm about to show you. This was led by Julianne Del Canton at the University of Washington. She's now in New York, and we are part of that team. So there's Andromeda again, this little speck there, 2.5 million light years away. That arc across is the arc of our Milky Way, and we're going to zoom in. So I'll remove the labels so you can focus on the on this image of Andromeda and this arc of the Milky Way. As we zoom in, fasten your seat belts because we're going to zoom a long way in. You'll see the companion galaxies of Andromeda right there. But as we zoom in, you'll be able to see individual stars in the Andromeda Galaxy. You can sort of see them now. You can really see them now. This is not a painting. It's not a digital image that someone's made up. It is a digital image, but the artist is the Hubble telescope. So this is an actual image, set of actual images stitched together into a mosaic. And the individual stars you see and the star clusters you see, this is a bright star, but you can see families of stars, like if you can see my cursor, this is a family of stars right there, another family of stars there. You can see bands of gas and dust. This is in the Andromeda Galaxy, all of this. So it's provided, this Hubble survey has provided a great insight into Andromeda and by vicariously of our own galaxy as well. Now, galaxies do something else. They're made up of stars, they're made up of dark matter, but they also collide with one another. And I'm going to show you a computer snapshots of galaxies colliding, computer simulations and actual snapshots. So let me remove the labels so you can focus on the video. Two galaxies, as they come together, we'll pause at certain points, like here, we'll pause the simulation. Here are two real galaxies that are about to collide. We go back to the computer simulation, the galaxies continue to spiral closer and closer, and they start to intersect each other at this point in time. Now, it might look like one is in front of the other, but if we stop and change our perspective, you can see that they're actually intersecting. And we pause. These are two real galaxies that are intersecting. Not the first pair, but a different pair. We go back to the computer simulation, and each galaxy stretches the other out using their tidal forces, differential gravity. And here are two real galaxies that are doing that to each other. Okay, so computer simulations, back and forth between computer simulations and real galaxies. So the two main bodies of the galaxies are coming back together, and right before they merge, we stop, and you get the point. Galaxy collisions are beautiful, and we can understand why they look the way they do through computer simulations. You might wonder, why does he care? Andromeda and the Milky Way, they're going to collide. It's because this is not just happening to other galaxies, the Andromeda and the Milky Way. There's Andromeda in the upper left, there's the Milky Way. We discovered in 2012 that Andromeda and the Milky Way are headed for a collision with each other. This is 10 years ago. Now, it's not a collision that's going to happen in 10 years. Otherwise, it would be happening now. We discovered this in 2012. It's going to happen in about 5 to 7 billion years. So let's see what the sky will look like in the future. the future Andromeda Milky Way galactic collision. This is a publicity video NASA put out because these were measurements with NASA's telescopes. Okay, so let's look at Andromeda will get bigger as we go forward in time. You know, astronomers wondered why Andromeda was getting bigger and bigger, and then it hit us. So, like I say, 4, 5, 7 billion years, the two galaxies will destroy each other, and they won't have this beautiful spiral structure, neither will. You'll have a blob like that. It'll be an elliptical galaxy. We have a name for it already. It's going to be called Milky Way Andromeda. And elliptical galaxies like this are common, and they're thought to be the product of galactic collisions. Paul, Ellie, can I take 5 more minutes to wrap up? How's that? Okay. One thing that the simulation got horribly wrong is the mountains haven't weathered in 7 billion years. I'm going to skip through this, although, how can I skip this image? This is a silhouette of the supermassive black hole that's at the center, not the one that was released recently, the one released pre-pandemic, of light bending produced by the black hole at the center of one such galaxy merger, M87. It was taken not with one telescope, but a series of radio telescopes distributed around the Earth, as you can see there. Now, light can be bent in wonderful ways. Look at this beautiful smiley face. The two galaxies have bent the light of background galaxies. And the person who predicted this would happen was none other than Albert Einstein in 1912. You can barely read this. This is an embossing on the photograph, 1912. And Einstein came up with a theory that says, don't think of gravity as an invisible force. Instead, think of it this way. Every object with mass, including the sun, you and me, every object with mass distorts space and time in its vicinity. And when you have distorted space and time, there's no choice but for everything to move in a bent path through that distorted space-time. Light, other galaxies, other particles, everything has to move in a curved line. That's how Newtonian gravity is expressed in Einsteinian gravity. Think about it as the curvature of space-time. Now, I have this picture up here because I study gravity and galaxies. But the person on the upper right is someone who's really instrumental in taking Einstein's theory and coming up with the notion of black holes. This is Karl Schwarzschild, Einstein's collaborator. Unlike Einstein, Schwarzschild died very young, died in World War I. His son, born in that year 1912, Martin Schwarzschild, went on to become an astrophysicist like his father and like his father's colleague, Albert Einstein. The family escaped from Germany during the period between the two wars, and Martin found himself as a professor at Princeton University, where he was one of my mentors. So Martin remembers Albert Einstein visiting their home after his father had passed away, and of course reconnected with Albert Einstein when Einstein also came away to the US and found his way to Princeton to the Institute for Advanced Study. I met 3 other people in Princeton who knew Albert Einstein: Lyman Spitzer, John Wheeler, and Freeman Dyson. They all knew Einstein. They met him at conferences, but they became his colleague when he came to Princeton. Martin's the only one who knew Einstein when Einstein was fairly young. Anyway, he's my 1 degree of separation to Albert Einstein, one of 4, and I'm your 2nd degree of separation to Albert Einstein. Another famous person, I told you I'd talk about people, is Stephen Hawking. He studied how particles can not just be captured by black holes, but can also escape from them. So Hawking radiation is something that Stephen Hawking and Jacob Bekenstein before him came up with. And I had the privilege of listening to Hawking in a room not much larger than this. That was several years ago in Santa Clara, where he was already completely confined to a wheelchair, of course, and using a voice synthesizer. But still, it was special to be in the same room as him. I'm going to put up pictures of 3 other people. There's Vera Rubin, the discoverer of dark matter. There's Chandrasekhar. What's special about Chandrasekhar? Chandrasekhar is my great-grand, not father, a great-grand doctoral advisor. So my doctoral advisor is Jim Gunn. Actually, Jim is one of my two doctoral advisors. Jim and Tony were my doctoral advisors. Jim's doctoral advisor was Guido Munk, and Guido Munk's doctoral advisor was Chandrasekhar. She's another famous person, and I had the privilege of meeting Chandrasekhar. I had the privilege of being mentored by Vera Rubin. I had the privilege of meeting Chandrasekhar once when he came to Princeton, and I had the privilege of meeting this person, arguably more famous than the other two, Mother Teresa. I met her for 30 seconds when I was a college student living in Calcutta, which is where she also did her work. In different ways, they've been role models for me, in different ways. I'm not going to talk about gravity waves here in the interest of time. I just want to talk about how the Milky Way and other galaxies, where they came from is from early, very, very early in the history of the universe. So you've heard of the Schrodinger Cat Experiment, in which you have radioactive material, and if you close the box, all you can say is there's a certain probability that the cat will be alive, like that, and a certain probability that the cat won't be alive. But you can't predict the fate beforehand. So this quantum uncertainty, which is, determines whether an alpha particle would be emitted, actually affects macroscopic things. The cat in this example. This is a thought experiment. This was never carried out by Schrodinger. As they say in Hollywood, no animals were harmed in the making of this experiment. However, nature carried out its own version of the Schrodinger Cat Experiment, where shortly after the Big Bang, there were quantum fluctuations. And like that Geiger counter, there was a period of rapid expansion where microscopic things became macroscopic things, and those tiny fluctuations turned into galaxies under the influence of gravity. Today we can see those fluctuations, the microscopic versions, post-inflation, and this is what they look like. These are actual ripples in the cosmic ocean imaged with radio telescopes. So these ripples, what happened to them was they grew under gravity. There was no music in the universe, contrary to what you're hearing here. But these ripples grew under gravity to turn into galaxies over time. You can see time counting up in the upper right. GYR is billions of years, giga-year. Okay. And 500 kiloparsecs is about 1.5 million light years. Just to give you a sense of scale. So these are sophisticated computer simulations to figure out how tiny fluctuations turned into galaxies. But today we know that these tiny fluctuations, some hotspot somewhere, turned into an infant galaxy that merged with other galaxies to form large galaxies. Within it there were stars. Some of them exploded. Those elements were reined in by the gravity of its host galaxy, but were injected into the next generation of stars and planets. There were wonderful, complex elements and beautiful life forms. That's my story, and I'm sticking to it. Thank you.
Okay, so I think we have maybe 5-10 minutes for questions. And a warning, you've probably gathered on the way up, the mountain is making its own weather this evening. So it may be hit and miss with observing. But we do have other lectures following this and a time schedule to get through. So I'm afraid we are going to have to limit the questions a bit, but maybe Raja will be here after his second lecture as well. So if anybody has a question for Raja, please raise your hand.
Yes, please.
Picture of that your students were mapping out how far away the stars were, and there were circles and triangles. What were the difference between those?
It was really very observant of you. So what it is in that particular picture is the circles were things that we were absolutely certain were Aralari. The triangles were somewhat more marginal. So we are trying to follow up the triangles to see if they really are Aralari. So we wanted to be fair to the viewer and say that these are the things we're absolutely sure about. And you would have noticed that the circles were the secure ones. One of the most distant ones is a circle, and there's one slightly further than it. The second most distant one is a circle, and the most distant one is a triangle. So we think that even the things that are marginal detections, discoveries. With a little bit more analysis and more data from the telescope, we'll be able to tell whether it's something else masquerading as an Aralari. There are other things in the universe that vary in brightness that can masquerade as Aralari, so that's what we're trying to tell them apart from. You are an astronomer already with that observation. Yeah, you are. Anyone else? I saw that hand first. Let me go there, and then here, please.
Yeah, when you showed the optical image of a collection of galaxies, how can we be sure the color of a galaxy is because of the surface temperature of the stars within the galaxy? Can also be due to maybe the redshift due to the expansion of the universe, right?
Yeah.
Can make the galaxy look lower in frequency.
Right, that's exactly right. So you're absolutely right that it's a combination of factors that leads to the color of a galaxy. There's at least 4 things. One is the age of the stars. That's one of the things I mentioned. One, as you said, is redshift, is how things are. Redshift, contrary to its name, doesn't make something look redder. It just shifts all of the energy to longer wavelengths. And what you're seeing there is a ratio between red light and blue light that's producing that color image. So it's not immediately obvious, unless you know the details of the galaxy and the redshift, how it's affecting its color. The third and fourth things that affect the color of a galaxy are its chemical composition. The more chemically enriched something is, the redder it looks. And the fourth thing is the more dust there is. You saw dust patches in Andromeda. Dust tends to absorb blue light more efficiently than red light, so a dusty galaxy could look redder and therefore look older than it actually is. So you're absolutely right that disentangling these 4 things, we can disentangle some of these 4 things more easily than others. There was another question. Yeah, please.
In this explore, he said like there's heavier elements come out. Why is that heavier elements on the planets where the new stars are collecting over the hydrogen?
Let me see. I'm not sure I completely understood that. So, heavy elements are produced in the interiors of stars. The sun will do that. The sun is going to die with those elements in its interior. Okay, in other words, it'll go through near the end of its life, it'll produce everything up to carbon, nitrogen, oxygen. It'll do that, but it'll die as a white dwarf star. So that carbon, nitrogen, oxygen will remain locked in the sun and won't be available to the next generation. But when you have an exploding star, the power of the explosion takes those elements and disperses them. Was that your question? Or?
My question is, when the exploding star spews out all this heavier carbon and oxygen, why did they end up in only planets? Why not new star, most of that?
No, so that's it. Both of those things happen. So these heavy elements get injected into clouds of gas and dust that are surrounding the exploding star, and out of that cloud of gas and dust, both stars and planets form. Not just planets, both form. So the sun has quite a bit of these heavy elements, just like the Earth has. Okay, so it's not only the planets that have them, but the stars as well.
So we talk about galaxies as being disk-like structures, but if we think about like planetary objects or stars as a spherical, so what makes it that galaxies are more disk-like rather than being spherical?
Great question. So not all galaxies are disk-like. When the Andromeda and Milky Way collide, what you end up with is something that looks more like a sphere. It looks like and if you think about the motion of stars in such a galaxy, it looks like a swarm of bees around a hive. Every star is going around the common center, but they're not all aligned in orbit. So elliptical galaxies behave like swarms of bees, whereas disk galaxies, like the Milky Way and Andromeda, as they currently are, look like solar system. Everything is moving in a plane. It really has to do with this notion of angular momentum, the amount they're spinning. And it's really the spin that flattens things. And the best way to see this is next time you go to a restaurant, make sure it's a pizza restaurant, make sure you can see into the kitchen, right? You'll see this person spinning the dough, and it's the spin that produces that flat disk. So it's the Milky Way. Before it became the galaxy it is, Andromeda before it became the galaxy it was a ball of gas and dust. It had some torques for neighboring galaxies that caused it to spin. They spun up because of gravitational collapse, there's a conservation spin velocity multiplied by radius is conserved. So when something's radius shrinks, it spins up. In the same way that an ice skater spins up when they bring their arms close to the axis of rotation. Okay, so that's conservation of angular momentum. And then that rapid spin really flattens things out. Okay. Are we done with the final question? Go for it.
In the beginning, you mentioned that the cosmos is an interplay of dark matter and dark energy.
Yeah.
You talked about dark matter, but could you elaborate a little bit about it?
Yeah. Absolutely. So dark energy is something that was discovered a little over a decade ago when people realized that the universe's expansion rate is not slowing down, which it should be because of dark matter, but it's speeding up over time. And like many astronomers, I didn't believe it initially, and I hated it. So in fact, I would make jokes about this. I would say dark matter sucks. Dark energy is truly repulsive. So if you remember that, that's what I mean by tug. One is trying to pull things in, and the other is trying to push things out. Dark energy, another way to remember it is it's anti-gravity. It's outward pressure rather than an inward pull. And this is empirical evidence for it in the expansion history of the universe.
Okay, I think we have to draw a line under at this point, but let's thank Roger again.
Thank you.